Between now and probably the start of year 11, you've attempted a trig solve on the calculator and seen this output. So what we're going to today is interpret this output a little bit more. Let's see what happens. So what I'm going to do is swing in GeoGebra here, and I'm going to graph two functions, f of x equals cosine x. So there's cosine. And I'm also going to graph a second function, g of x equals a half. Now, when we're attempting a solve, what we're saying is when will cosine x equal a half, or when would f of x equal g of x? And if we don't say or specify a domain, what we're going to note is that they're equal to each other here. They're equal to each other here, 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 here. And maybe you get the point that there's actually infinitely many times it will equal a half. And if I go in the other direction, same thing occurs there, etc., etc. So what happens is we've got to forgive the calculator for not being able to give us a finite number of solutions for this because we haven't told the calculator where to look. Okay, so what it's attempted to do is give us every single solution, or what we call the general solution. So no domain has been given, so cosine x will equal a half infinitely many times, and rather than commence listing all the solutions, the calc just gives you a general solution. And let's try to produce one on our own. So we're going to try and solve cosine x equals a half. And what I do is I actually just try to proceed with the solve as normal, as if it was a restricted domain. So the first thing I'll do is generate my base angle, which that will be pi on 3. Then go to my unit circle. There's pi on 3, which will be a half. And the other time it'll be a half is at, what's that? That's 5 pi on 3. Okay. So I can start to then produce my general solution. So it's x is equal to pi on 3. And then what I'm going to do is be able to generate subsequent solutions after that by going around again, by moving one complete revolution around, and I'll get another solution. So what I'm going to say is, and you can get another solution by adding 2 pi. And how many times do you want to go around, or which solution do you want? Do you want the first solution in the positive direction, the second solution, the third solution, etc., etc., the 0th solution or the first solution? I don't know which one you want. So what I'm going to do is declare a variable there, n, okay? And what I've got to do is specify a parameter on n. N is an element of z, okay? And z is all the whole set of integers like 1, 2, 3, 4, 0, -1, -2, -3. Okay, so that's what z actually is. So that's one way to generate the solutions, is to start at pi on 3 and just keep adding whatever many 2 pi's that you want to add to get your solution that you desire. Now we can also do this at 5 pi on 3. So we're going to go 2 pi n, where n is an element of z. Now, there's a more elegant way to actually write the solution to this as well. And note that I could go to pi on 3, or I could get to this same point here by moving backwards pi on 3 as well. So I could actually write that in a more elegant way as x is equal to plus or minus pi on 3 plus 2 pi n, where n is an element of z. Now that's acceptable, that's perfectly acceptable. This is just like, it's good looking, all right? It just is neat. So that's the important thing. So you could perfectly legally, well, not legally, it's not like illegal if you don't, but it would be just fine to produce that as an answer to this question here, but it's with a little bit of elegance and swagger that you would produce that one. Each will get you full marks, so don't fret. Right, so there's my infinitely many solutions to this particular question, okay? Now, if we go and have a look at the problem up here, we can see basically how we would do it, or how we could interpret it. That's 2 pi n take pi on 3 would be the first solution, and that's the equivalent to this one down here, negative pi on 3 plus 2 pi n. So all you do when you see this constant 1 value, replace it with n and you get your general solution. This question also shows the importance of being able to be flexible with general solutions or read different ones. Like you might solve this and the calculator says this, but the answer to a SAT question or a multiple choice question might be this one here. So you need to recognize that these are the same. Okay, it's very important. Right, let's go to another problem. Okay, so what we're going to do is solve this one. Okay, so the next one is cosine is equal to a half. Okay, so this is the same base angle, is pi on 3. Okay, but this time what there is there's a translation. Okay, so what we're going to do is write our first general solution. So let's pop that in. That's pi on 3 over there, and our second one was 5 pi on 3. So x is equal to pi on 3 plus 2 pi n, but it's not actually x. Okay, it's x take away pi on 3 that we've just solved for. Now what we've got to do is we've got to actually add the pi on 3. Okay, so this is a really interesting case here, and I'm like, it's not surprising that I've pinched this example from Mr. Tench, and I'm not surprised that he did this one because it looks really similar to the previous one, but there's a unique thing that happens here. All right, so what I'm going to do is add pi on 3. Okay, now here's my answer. X is equal to 2 pi on 3 plus. Now what do I do with this period? Do I add pi on 3 to this period? Well, the answer is no. Okay, the period is exactly the same. What we're actually just doing is saying because of the translation now, what you're going to do is generate solutions every 2 pi on 3, but you're still going to have to go around 2 pi. So whenever we do this and solve for the translation or the horizontal translation, what we do is we just keep this period exactly the same. So it's just the kind of base solution that actually changes, because that's all we're shifting. It doesn't actually equal it at pi on 3 anymore. Because of the shift, it's going to equal it at 2 pi on 3, so 2 pi on n. Now, our other solution was x is equal to 5 pi on 3 plus 2 pi n. We could have also written it as negative pi on 3 plus 2 pi n. So if we take this one, what we could do is rewrite that. X is equal to 2 pi n. So I'm going to add pi on 3 to it, okay, which will mean that that's 0. So we can just say it as 2 pi n. Or I can add it to this one here and say it's 2 pi plus 2 pi, which is 4 pi. That again would be equally legitimate. Okay, so there's a number of different ways that we could write these two solutions. Notice though that if we use this previous version of the combined solution and then had to add the pi on 3, we'd have to break this solution apart. We can't use a plus minus anymore on that one. All right, so there's my two solutions. So these are the two solutions here. So I'm going to put a, well, I forget what that squiggly brackets, I don't know what the technical term is for that, where n is an element of z. So again, just got to define what n is each time. Otherwise, if you don't define it, that means that well, what can it be? Is it any element from the real number system? Like, can I get a solution 1.5 times around the unit circle? No, I can't. It's only the integers. Alrighty, let's go to tan now. Okay, so what we're going to do is solve this. So tan is equal to, or tan 3x is equal to 1 on root 3. Now that one is, if I just draw this up, we've got 60 there, which is pi on 3. We've got 30 there, which is pi on 6. That's 2, that's 1, that's root 3, okay? And so what we're looking at here is 1 on root 3. So we're going to go pi on 6, opposite over adjacent. So our base angle is pi on 6. That's probably the only one I still really need to use the triangle for. The rest of them I can seem to remember, but that's the only one. I asked Mr. Tench, I think it was last year, whether or what the tan of 1 on root 3 was when I was doing a particular question, and he goes, I don't know, use the triangles. So he wasn't trying to be rude, I don't think, but emphasizing the fact that you just don't have to memorize these things. Anyway, I'm rambling now. So the base angle is pi on 6. All right, so that's that, where we're going to generate a 1 on root 3 tangent intersection. Okay, Now, when is it going to happen again? Okay, so what's going to happen is with tangent, it's going to happen over here. Okay, so what we're going to do is note that this would be 6 pi on 6. It's going to happen at 7 pi on 6. Okay, but what we would be doing is just simply adding pi each time. So if I added pi and then pi and then pi and then pi, I really don't need to break this into two separate solutions. So here's my solution here. 3x equals pi on 6 plus pi. Okay, I don't need to include a separate one for 7 pi on 6 because if I'm adding pi, I'm going to get to the second solution. Okay, and then I'm going to get to the next solution and the next solution and the next solution. So I can summarize the general solutions for tan with one particular equation. Now I'm going to put n because n allows me to specify the value. Okay, so I've solved for 3x there. I need to solve for x. So what I'm going to do is divide by x. X is equal to pi on 18 plus. Now, what do I do to the period? Because in the last question, what I did was I chose not to add that value up there to the period. So have a think about it. Pause the video if you want and make a prediction about what you're going to do, i.e. do you divide by the 3 to the period or do you not? Okay, well, hopefully you went for the answer that you do divide by the 3 for the period, because to generate the solutions, I've also got to adjust the period, okay? Because now we're starting at pi on 18, and if I add pi to it, I'm going to end up like down here, okay? And that's not going to get us the solutions we're after, okay? So what we want to do is absolutely change the period as well. So we're going to go pi n on 3. All right, now your calculator will do all sorts of things on this one here. It'll modify those and simplify up the fractions. So don't be scared if you go a solve on the calculator and you find that what you provided was completely different to what the calculator got. 1 on shift root 3 for x, please. Well, that's sort of an anticlimax because it was literally exactly what the calculator did. So it didn't combine them. Anyway, bad example there by Mr. Miller, but yeah, a lot of times I find that the calculator will produce something different to what you end up producing. Anyway, it didn't on this occasion. All right, this last example, we're looking at when two functions intersect each other. And don't be deceived, this is just a simple equate them. Okay, so we're going to let f of x here equal g of x. And it just so happens that g of x happens to be root 3 on 2. Like, why that random value? Well, it's because when we attempt to solve on this, we know an exact value for root 3 on 2. Okay, so let's go our base angle, which for root 3 on 2 is going to be, oh my God, I'm picturing a unit circle in my head, and that is pi on 3. So pi on 3 will get us a root 3 on 2 for sine, and over here it'll also get us one at 2 pi on 3. Okay, so let's go ahead and write up our first general solution. So that's x equal to pi on 3. Now I've just done something silly there, and I've just written x. I've solved for x, take pi on 3 equals pi on 3. Plus we've got the sine function, and sine functions without a period change will generate solutions every 2 pi, and I want a general solution, so I'm going to pop an n in. Right, so there's our first solution. Our second one is going to fall out at 2 pi on 3. I'm going to write x equals x take pi on 3 equals 2 pi on 3 plus 2 pi n. Now what I'm going to do is write my solutions. X is equal to 2 pi on 3 plus 2 pi n. And that one is going to be 3 pi on 3, or x is equal to pi plus 2 pi n, where n is an element of z. All right. Yeah, nothing much else I can do with that one. To collect up the pi's, I would have to have pi n here to say that that's 3 pi n. So just be careful about your algebra on that one. This one wasn't in your notes, but I thought I'd give you a look at how VCAR would assess a problem like this. It is on one of Ms. Cowan's worksheets. So I will get you to do the problem as you would if you were doing her worksheet. So pause the video now and have a go at the problem, and then unpause it and see how you go or how you went with it. All right, so what we're doing is the general solution to this. So we want to know when sine 2x is equal to -1. So sine is equal to -1 there at 3 pi on 2. So let's go ahead and so what's going to happen is if we go around the unit circle one more time, it's always going to be at that one spot, that 3 pi on 2. So I could say 3 pi on 2, and then it's going to happen one more time around at 6 pi on 2, but I don't need to generate that next solution. So what I'm going to do is say that x is equal to, 2x is equal to 3 pi on 2 plus 2 pi n. Okay. Now, x is then going to equal 3 pi on 4 plus pi n. All right, let's see if we've got a winner. Wrong period. Power of n. No idea what that means. One solution. Different period. No. This is the only correct answer, or the only one possible. Now, why? Okay, so what we've got here is 3 pi on 4, and the difference is that they've got negative pi on 4. If you understand what's happened here, it's important to note. So a unit circle has a standard period of 2 pi, but what's happened because of this dilation factor is our period is now pi. And what happens is all of these values around the unit circle change. This is now 3 pi on 4 because of the period change. All right, and what that means is to get to 3 pi on 4, I would go all the way around the unit circle. So from 0 to 3 pi on 4. But actually to get there, I could also go in the reverse direction and I would go negative pi on 4. So this solution here could equally be written as negative pi on 4 plus pi n. N is an element of z, which is option A. Okay, so tough little problem there for question 4. And again, you see that they've got some good gear even in the early stages of the multiple choice.